in a way lah. That's what we are doing. So there will be a lot more maths in the next slide. So for those of you who just came in, this is the code. Take it down first. Okay, let's go to the next slide. Alright, so here we are looking at the entropy chapter. Okay, so again, like I said, this is a more mathematical slide compared to the previous one. So in this slide, our objective is to apply the second law of thermodynamics to processes. We will define a new property to do so, which is what we call the entropy. And then we will learn a principle that is called the increase of entropy principle, and you will learn how to calculate entropy changes for pure substances, incompressible substances, and ideal gases. And then we will look at a special case of idealized processes called isentropic process. So now you get one extra process called isentropic process, and we will develop some property relation to this, and then you will derive work relation and isentropic efficiency for various steady flow devices. Okay, just a short recap. So in the first law of thermodynamics, once again, we talk about conservation of energy. So the equation that we established there was delta E equals to E final minus E initial system. And then when we went into the second law chapter, we mentioned that energy not only has quantity as defined as in first law, energy also has direction. So so when the energy change from one type to another, there is a direction to it, and it is determined by the quality. So this direction-wise thing, we use entropy to determine basically whether that direction is possible or not. Okay, so entropy is not a conserved properties. So that's why we have a principle called increase in entropy principle. So for entropy, basically if you involve entropy change, then that process is not reversible. Okay, so first off, we will derive what we call the Clausius inequality. So this is something that is first stated by a German physicist called Clausius. That's why that's the name. Okay, so this statement states that the cyclic integral delta Q over T is always less than or equals to 0. So if you integrate this term delta Q over T over the cycle, that's what we mean by cyclic integral. So over the entire cycle that it goes through, the value that you get will always be less than 0. So for a change in cyclic process, the net change in heat or work is never equals to 0. And the net change in any properties will be 0. Does that make sense to you? So in a cycle, the net change of heat or work, meaning your Q net or your work net, those values will never be 0. Right? They will cancel each other off. They might cancel each other off depending on the assumption that we make, but they will never be 0 individually. But the net change in property is always 0. Why? Because if you are dealing with a cycle, you start from state 1, it will always end back at state 1. So meaning, if you just look at the overall case, the property is as if that it has never changed. So the integrals only depends on the state. So you can see from that. So integral is always depending on states. So meaning if you are integrating it over the cycle, is something like you are integrating state 1 initial, but final state is also state 1. That's why the minimum value is always, the maximum value is always 0, like it will never be more than that. So therefore, this is a property. Okay. So from here, he obtained a new property called entropy. So entropy change the general equation, as you can see here. So ds, the general equation is always delta Q over T. That is the general equation. Of course, there are a bit of variation depending on what kind of situation that you are looking at, but entropy wise, it is always delta Q over T. So you can see that this property is slightly different from your normal property that you are used to, because usually when we talk about enthalpy, we talk about internal energy, they are all energy. Entropy is in terms of per Kelvin, so it's energy for the particular temperature, basically that kind of meaning. The energy change for every degree, every Kelvin or every degree Celsius. Okay, so the delta Q in this case is referring to the heat transfer between the system and the environment. So as you can see from the diagram over here, so this is the delta Q that we are talking about. So delta Q is the differential heat transfer, or the heat transfer between the system and the surrounding. Then T is the absolute temperature. So once again, as you can see here, it's always in terms of Kelvin, at which heat is transferred. So depending on which part that you are looking at. For example here, like again this diagram that we were looking at just now, you can see that we have two different temperatures here, right? 20 degrees Celsius and 30 degrees Celsius. So the T will depend on which side you are looking at, meaning whether you want to look at the entropy change of the environment or the entropy change of the system itself. So then that will decide which temperature you use for that T. Again, this will be a bit more clear when we look at example later on. Alright, so here we try to prove what he mentioned just now, which is delta Q over T is always equals to or less than 0. So consider a heat engine. So now we talk about a heat engine. So do you still remember what's a heat engine? Something that generates work from heat energy. So that's what we call heat engine. Okay. So over a cycle, so we define just now what we said just now. So sorry. So we define this with the just now the cyclic integral over delta Q over T. Then when you have a standard heat engine, so something like this. This particular thing is your heat engine. Okay, and this system is where it receives heat from the heat engine. So if you integrate the heat engine over the entire cycle, then it will be QH over TL, H over QL over TL. Okay, so the change in the heat of the heat engine will be the QH and the QL. That will be the difference. So if we are dealing with a reversible one, if we are dealing with a reversible heat engine, remember that we have this relation. We mentioned that if you are dealing with a reversible heat engine, QH and QL can be replaced by TH over TL. So if we replace that, then obviously it means that this whole thing can be cancelled off. So you will arrive at the conclusion where delta Q over T is equal to 0. Makes sense, right? The first one. So the change in the heat over T will be QH over TH minus QL over TL. If you replace the entire thing with QH over QL equals to TH over TL, you will find that QH over TH is equal to QL over TL. That's why the change is 0. Now, let's say if we are looking at an irreversible HE, heat engine. Okay? So when you're looking at an irreversible one, let's assume this remain constant, because that's how much heat you are receiving from the high reservoir. How much the reservoir is losing heat, it does not matter to us, right, in this case, because we are only looking at the heat engine. But when we look at the heat engine itself, the heat engine itself might lose some heat to the surrounding when we are not talking about an ideal case here. So let's say if we lose some heat to the surrounding this way, then this QL value will drop. It will not be as the QL value will not be as high as the previous value, right? But TL value will still remain constant. So which means overall this thing will I a bit off here. I'm explaining through the other direction. Okay. Come back again, okay? So this one will be a constant value. We need this one to be higher. That will be a constant value. You will still get Q loss, but the Q loss we put over here. I put it at the wrong place. Meaning your system will still lose more energy, which result in less work, which result at less work net. Okay? The non-reversible system will lose more heat and result in less work generated. Okay, makes sense, right? Sorry, just now I was categorizing the heat at another thing. It shouldn't be that case. So meaning the heat that it will lose, or rather the heat that the system will reject, is supposed to be higher, which is supposed to, there should be more heat loss. So meaning this will increase. So if this entire value increase, then meaning when you minus off, then this term here will become a negative term. Because in the previous one, in ideal case, is 0. So in this case, if your QL increases, then the integral will become negative. And which is why we can define this whole thing as less than 0. Okay, so this is just the inequality statement that is being stated here, alright, by this clauses. Okay, so now we try to look at increase in entropy principle. This few section will be slightly more confusing. So try to, maybe if you don't understand, just let me know. Because sometimes we keep saying that it's increased, but then somehow you will see that you will have negative value. So, alright, so here, when we talk about increase in entropy principle, the system that we define needs to include the surrounding. So meaning usually when we define our system, we only talk about here, right? But here, if we want to strictly look at the increase in entropy principle, we need to look at how the entropy of the environment change as well. So that's why here you can see that the system and its surroundings form an isolated system. So meaning we look at what happened to the immediate surrounding as well. Then we form a bubble over here. So this is our new system. So instead of like what we used to do, we don't look at just the thing, we include the immediate surrounding. So this entire thing is a system, and we assume it as an isolated system. You can also imagine it as things like, remember when we say that if you are rejecting heat to a reservoir, the immediate surrounding will have some changes. But in the long run, if we go further, so for example, aircon, you are looking at the outdoor unit. If you stand near it, it's very hot. But if you just step a few steps away, actually you can't really feel the effect anymore. So it's the same thing. So now you form a bubble over that area where you can feel the effect, and that is where we are only looking at. So the heat transfer for an isolated system is 0. Yeah, so you are standing right outside here, so you can't feel anything anymore. And the entropy of an isolated system. So now we are talking about the overall entropy of this entire system here. During a process, the overall change in this entropy will always increase. This is the principle. So, or it will remain constant for a reversible process. So, we end with this one. So, the delta S isolated, so the change in the entropy of this entire system will always be more than 0 or equals to if you have an isolated system. Okay, so what we are trying to say here. So let's see in the next slide. So a total entropy change of an isolated system is the sum of entropy change of the system and its surrounding. So this change in entropy that we are talking about is the change in this entropy and also the change in the entropy of the surrounding. Remember just now I mentioned when the T that you choose, it depends on which part that you are looking at. So these two sections will have slightly different temperature depending on. So here the S generated is equal to the change in the total S. So S is entropy equals to the change in the entropy of the system plus the change in the entropy of the surrounding. And this entire change, so actually this is equal to this. We are talking about this one, will always be more than or equal to 0. So entropy will always be, you will always be generating entropy. This is what we are trying to say. Okay, so if you are dealing with a reversible process, no, sorry, this one actually is if you are dealing with an isothermal process, a reversible isothermal process. So if we are dealing with an isothermal process, then the delta S is actually easy. You can actually determine this easily because the delta S itself is just Q over T naught. Because the T won't change, it's just a fixed value, then regardless of what Q you are dealing with, then it is just Q over T naught. So this equation is particularly useful for determining the entropy changes of thermal energy reservoir, which is actually what we did just now when we were deriving the closest inequality. Because we just use Q over T and Q over T. Why? Because we learned that thermal reservoir temperature will never change. So the heat that you take from it, let's say is a constant value, the heat that you reject to reservoir is also a constant value. So then you can just use Q over T naught. So this can be used to determine the entropy change of thermal energy reservoir that can absorb or supply heat indefinitely at constant temperature. So assume isothermal process, and if you use second law of thermodynamics, so here this is where things will get a bit confusing. So just now we mentioned that entropy will always increase, right? But actually if you just look at the system itself, if we ignore the surrounding, you will see that entropy actually can decrease one. Because here, if we just follow what you learned in second law, heat out is negative, heat in is positive, right? So if let's say we are just looking, so here, this will actually be Q over T. This value can never be negative because we are using absolute temperature. But this value, here this is a positive case. But this one, Q over T, this is actually a negative value if you are removing the temperature. Again, this cannot be negative. Or rather, this will always be positive. This will always be positive. So if you only look at the system, so remember just now we try to define, we include the surrounding. Here, if you only look at the system itself, you can get negative because Q out is negative value. So either way, when you put into it, entropy actually decreases in this case. Okay, so here we look at two special cases. The first case we have talked about it. If you have isothermal process, then delta S is simply Q over T naught. The change in the heat over the temperature. Now, let's say if we have adiabatic process. Okay, so if you have an adiabatic process, meaning we don't have Q value, right? If you don't have Q value, meaning the change in entropy is actually 0. This is actually what we call an isentropic process, which is a constant entropy process. So technically speaking, isentropic process is an adiabatic process. Because entropy, as you can see from the equation itself, Q over T, entropy is primarily caused by heat change. So we just define a new process called isentropic process. Essentially, it just means adiabatic process, but it is useful in the case where, in the sense that whenever we mention isentropic process, you should immediately think about S doesn't change. Because when you talk about adiabatic process, that might not be the case, as in you will not you probably won't relate it to constant entropy. But when we mention isentropic process, the first thing that it should come to your mind is that this process entropy doesn't change, meaning you can make use of it somehow. Alright, of course, how, we haven't learned all those things yet lah. But in this case, that is the case. So isentropic process is a constant entropy process. Okay, so here we consider, so let's say, so here previously we keep talking about a reversible process for entropy change. Now we look at irreversible process instead for entropy change. So consider a cycle here where we have two different type of process. Okay, so 1 to 2. So 1 is the initial state, 2 is the second state. We do not know what process it is, so we don't care also. As of now, we do not know and we don't care. So process 1 to 2, the dashed line here can be a reversible or irreversible process, while the bottom line is an internally reversible process. Okay, so now we use the closest inequality just now. So this equation here, we split it into two different processes. So 1 to 2 and 2 to 1, because you go to 1, then you come back from 2 to 1. Alright, now process 1 to 2, we say it can be reversible or irreversible. If process 1 to 2 is reversible, right, it will actually follow back the same line to go back to 1, because it will technically be the same process. 2 to 1 is just internally reversible, but technically it is still not fully reversible. So here you can see that for the internally reversible process, like I said just now, if it is not a fully reversible process, it will not follow the same path, meaning there will be some change in energy or entropy in this case. So we define it as the change in entropy. So we put a second process here as S1 minus S2, and then we move it to the other side. So it becomes this. Alright, so this is our delta S, which is here. So here from this equation you can see that delta S is more than or equals to delta Q over T. So that's why process 1 to 2 just now we say is either reversible or irreversible process. So if it is reversible process, then like I said, if 1 to 2 is reversible, it goes this way, it will follow back the same direction back. So then it will become, so the delta S will become 0. But if it is irreversible, then the value will be different, will be less than that. So then it will always be a positive value, basically that. So here, what we are trying to define here is that the entropy that you will generate is always equals to or more than 0. It cannot be less than 0. So some entropy is generated or created during an irreversible process. If you think about it this way, it also makes sense. So again, if we come back to irreversibilities, remember we mentioned that irreversibilities are like energy loss, friction, heat generated and stuff. So all of the irreversibilities actually will eventually lead to heat loss. So that's why entropy will always increase because of that, because you will always generate heat. And so S generated is always a positive quantity or 0. So now the confusing sentence just now. So entropy change of a system can be negative, but the entropy generation cannot. So again, if we have this one, delta S here can be negative. But if we include the surrounding, the overall change here cannot be negative. Again, it will be a bit, it's a bit confusing here, but we will see how it is later in one of the later example. Alright. Okay, so we talk about entropy a lot here. So why do we study entropy? Because processes can only occur in a certain direction and not in any direction. So the basic idea here is if the entropy that you calculated is less than 0, then it will tell you that this process cannot happen. basically that. It must be equal to or more than 0. So it is not a conserved property. It cannot be conserved, so it can only be conserved during reversible process, which again we know that doesn't happen. So performance of engineering system is degraded by the presence of irreversibilities, and entropy generation measure that irreversibilities. Oh, actually let me see. Yeah, actually this diagram here shows how, it doesn't really show you the calculation, but it does show you what we mentioned just now. So you can see that in this system, if this system is losing heat, let's say, so you can see that the entropy change for this system itself is negative 2. But in this case, of course, we got no proof because we haven't done any calculation yet. But in this case, the change of the entropy of the surrounding is actually 3 kilojoule. So this 3 kilojoule per Kelvin comes from the heat that you reject to the system. So you can imagine that the system is losing heat. At the same time, it means that the surrounding is gaining heat. And if you add these two up, then you get a positive value. So the surrounding one will always be higher in this case. Why? Because your surrounding temperature has to be higher than the system one. Oh wait, the surrounding temperature has to be lower than the system one in order for it to reject heat to the surrounding, right? Right, so let's look at one example here. So here we have a very simple example. It doesn't really complete the whole thing as well. So we only have one. So let's say now, in this case, so heat in the amount of 100 kilojoule is transferred directly from a hot reservoir to a cold reservoir. Calculate the entropy change of the two reservoirs and determine if the increase of entropy principle is satisfied. So this is actually pretty much like what we saw just now. So let's assume that this is that system that we saw just now, and this is the surrounding. It's the same thing actually, but we are assuming that the temperature doesn't change here. So the entropy change from this TH, this TL, you see both of them have the same temperature, right? So if you calculate the overall change in the entropy, you get QH over TH. You also get QL over TL. These two Q are the same value, but the temperature is not the same. So you can, same value, but not the same direction. So you can see that from the high temperature reservoir side, we say negative 100 because it is rejecting heat. And the temperature at the high temperature reservoir is 1200 Kelvin. While at the low temperature reservoir side, or the cold reservoir side, it is gaining 100 kilojoule. But the temperature of the low temperature reservoir is 600 Kelvin. So obviously you know that this value will be more than this value. That's why, which is why you end with a positive entropy change value. So since the entropy of everything involved in this process has increased, this transfer of heat is possible. So this keep with the increase in entropy principle. So let's say if you do this calculation, you found out that entropy change is a negative value, then meaning this process cannot happen, right? So which makes sense. If you just swap the direction, 600 Kelvin rejecting heat to 1200 Kelvin, then the value will be negative. Then it means that it cannot happen. That is what we use entropy for. Right, so this is just a simple example here. Okay, next we have another example. So entropy generation during heat transfer processes. So a heat source at 800 Kelvin loses 2000 kilojoule of heat to a sink at 500 Kelvin and 750 Kelvin. So let's say in both cases you are losing the same amount of heat. Determine which heat transfer process is more irreversible. So here we do the same thing for each of the temperature. So you can see that the source is losing 1200 kilojoule, and then this one is 800. So this is a constant value for both cases. The heat rejected to the sink, in this case, then will be 2000 over 500. So you total them out, you will get 1.5 kilojoule per Kelvin. So for the next one, then it is more obvious, right? Let's say if you calculate for B. B has the same heat transfer, but with a lower temperature. So it means that the generated entropy will be less. Makes sense, right? So here, generated entropy is 1.5, while in this case, generated entropy is 0.2. So what does these two calculations tell us? The one with the lower entropy will be more, so the term that the question uses is which one is more irreversible. So what does more irreversible means? Meaning it is further away from the reversible process, which means that it has more losses. So we know that entropy is a measure of irreversibilities. So meaning that the one with a higher entropy change value is more irreversible and it is less ideal basically. So the total entropy change for the process in part B is smaller and therefore it is less irreversible. This is expected since the process in B involves a smaller temperature difference and thus a smaller irreversibilities. Does that make sense to you? Alright, now we look at another example again. So example 3. A completely reversible heat pump produces heat at a rate of 300 kilowatts to warm a house maintained at 24 degrees Celsius. The exterior air, which is at 7 degrees Celsius, serves as the source. Calculate the rate of entropy change of the two reservoirs and determine if this heat pump satisfies the second law according to the increase of entropy change and principle. Okay, so this question, now, if I am not mistaken, let me see. Yeah, this question doesn't show you all the working. Okay, so now you need to look at this question one by one first. So the main term, keyword that you see here is a completely reversible heat pump, meaning we are talking about a reverse Carnot cycle here, or a reversible heat pump that runs on reverse Carnot cycle. So which produces heat at a rate of 300 kilowatt to warm a house. So let's say if you have the heat pump here, this is 24 degrees Celsius, it draws heat from 7 degrees Celsius. And this QH is 300 kilowatt. And it obviously will have a work in here. So you need to calculate the rate of entropy change of the two reservoirs and determine if this heat pump satisfies the second law. So again, I said this question doesn't show you the complete working, but you can see from the answer here that in order for you to determine whether this satisfies second law or not, obviously you need to find out what is QH over TH. This one, all the values are given, so you can see here. But at this section, QL over TL. So we don't have QL. So what do you need to do to get QL? So what to do? We run QL here, right? Actually, we just discussed this at the beginning of the lecture today. Okay, so you can see that it tells you that this heat pump is completely reversible. So meaning it runs on the reverse Carnot cycle. the COP will be equals to 1 over 1 minus, I forgot it's QL over QH or QH over QL, but should be this one. And then, so you can replace the whole thing with TL over TH in order to find the COP. Or rather, actually you don't need that, this one too long already. You can just do this. Because this is a reversible heat pump. So if it is reversible, then meaning the ratio is the same. So based on this, you can get the QL value. So once you get the QL value, then you calculate the QL value, QL over TL. And now you can see that they are the same value. So when you find the total entropy change, you will get 0. So what does 0 means? It means that this heat pump is completely reversible. And in a way, the question didn't lie to you. But yeah, we are solving this based on this thing. So does this satisfy the increase of entropy principle? Actually, yes. Because increase of entropy principle doesn't mean that entropy only increase. It means that it is either 0 or more than 0. It can only increase. Alright, then I will move on. Okay, so now we look at TS diagram. So previously, we keep looking at PV diagram, right? In the basically most of the previous chapters, everything that we draw are based on PV diagram, PV diagram, PV diagram. When we involve entropy change in our calculation, sometimes the more useful diagram to draw is TS diagram. Okay, but same thing. TS, PV diagram, these two we use them interchangeably. So the entropy change between two specified states is the same, whether the process is reversible or irreversible. We are just repeating what we said. So PV diagram, area under the graph, what does the area under the graph of PV diagram represent? In a closed system, it is boundary work. In a cycle, what if it is a cycle? It's actually still work, but it's network. Okay, so now PV diagram, so let's say we take out the term net or boundary. So under PV diagram, it represents work, right? In the TS diagram, it will represent heat transfer. Because you can see from the equation as well. Right, entropy is Q over S. Q over T. So entropy is Q over T. So if you move around, then you get this equation, right? So meaning the area under the graph of a TS diagram actually gives you net heat or heat transfer. So this gives you heat transfer. So remember this: TS diagram gives you heat transfer, PV diagram gives you work. So just some common sense thing here. If heat is added to a system, delta Q will be positive. So meaning delta S will be positive. Entropy increase. So you can see in this diagram here, roughly something like that. Temperature increase, S increase. If heat is removed from a system, then delta Q will be negative. Delta S will also be negative. So this will mean entropy decreases. If entropy remain constant, which is an isentropic process, then it will just be a vertical line because S doesn't change. So during an internally reversible adiabatic process, the entropy remains constant. Yeah, that's pretty much it. So no irreversibilities. So most of the time when we analyze an ideal cycle, this will be the assumption that we make. So meaning we will just assume that it is internally reversible, that there are no irreversibilities within the system itself, and then it is an isentropic process. Okay, so something for you to ponder. So first one, what does the area under the process curve in the TS diagram represent? We kind of talked about it just now. What does the area enclosed by a cyclic curve in the TS diagram represent? The bottom diagram. And what does the ratio of the area enclosed by the cyclic curve to the area under the heat addition process curve in the TS diagram represent? A bit long. Let's look at the first one first. First one, we just talked about it, right? Area under the process curve in the TS diagram is heat transfer. Then what does the second one represent? Area enclosed by a cyclic curve. In short, it's like this area. What does this represent? Not entirely correct. You need to think in terms of a full. Okay, think about it in terms of an internally reversible cycle. So you think about it this way. What will cause it to change from 1 to 2 and 2 to 3? Okay, or more rather, what is the area under the graph from 1 to 3 represent? Heat what? Heat gain, right? That's why entropy increases from 1 to 2 to 2 to 3. Temperature and entropy increases, so it's Q in. And now, then we come back. So 3 to 4, don't need to say anything. It's an isentropic process. So 4 to 1, what does this represent? Yeah, because 4 to 1 entropy reduces, it's a Q out. So, what does this area represent then?
Change in Q.
It's heat Q net. It's the change in Q, right? The overall change in Q. And so for a cycle, Q net is also equals to work net. Okay, so in a cycle, we assume that energy in equals to energy out. So Q net will actually equals to work net. So last one, what does the ratio of the area enclosed by the cyclic curve to the area under the heat addition process curve in the TS diagram represent? So meaning, what does this area over this area represent? So this, the red one over the blue. So what is the blue again? COP is for refrigerator cycle. Refrigeration cycle. Here we are talking about heat engine. Heat engine. Yeah. So actually it's efficiency, because the red area will be work net. The blue area is Q in. So this is actually an efficiency term. So just a quick one here. Why does this carry over here? So what you see on the left here is a TS diagram for a Carnot cycle. So for Carnot cycle, previously when we were talking about this in the previous slide, it was a PV diagram. Okay, so if you look at a TS diagram for a Carnot cycle, actually it's very simple. It's just a square. So all the expansion and the compression process, we assume them to be isentropic because it will always be like one process with heat addition, then one is work out, then the other one Q in heat rejection, then work in. So both of the compression and expansion process we assume isentropic, so it's just a square in the end, or rather a rectangle. Right, and then on the right is a HS diagram. So for adiabatic steady flow devices, the vertical distance delta H on an HS diagram is a measure of work, and the horizontal delta S is a measure of irreversibilities. Basically, that's how entropy and enthalpy change. Because again, entropy causes energy losses. So entropy would drop, enthalpy would drop because of that. HS diagram, usually we don't use it as much. We mostly use it to define a certain equation for entropy. That is all. Okay, I think you have heard the term entropy enough for now. I mean, we're still talking about entropy later, but let's have a 5 minutes break first. Then after that, we look at what is entropy. So actually, so far we haven't actually talked about what it actually is in real life.